Welcome to the Learning Chapter. In the Learning Chapter, we're going to learn about conditioning. Conditioning is the technical term that refers to the manner in which a person or organism acquires associations in the environment between stimuli and responses. It's a bridge between basic neurophysiology that we learned about back in Chapter 2 and the much broader aspects of social psychology that we'll be talking about at the end of the semester. Learning is defined as the process by which a relatively permanent change in behavior occurs. Now you see the word relatively permanent is there in capitals and italics, and that's because the main aspect of learning is that it always is changing. That is a key aspect of learning. It's all about behavior change, never stability over long periods of time like the retention of information, but rather specifically an adaptable component where you change your patterns of behavior. And in fact, as your environment changes, your behavior will change. So as the environment changes, new patterns of behavior will be learned. And then as your environment changes again, the patterns will continue to change. However, this does not mean that you forget anything. The aspect of remembering or forgetting is all related to memory. This specifically is related to whether or not behavior changes in accordance with the demands from the environment. So learning allows for the acquisition and the elimination of novel behavior patterns across different environmental conditions. And of course, environmental conditions will change over time themselves, so there's always a basic aspect of learning involved. Back in the neuroscience chapter, we talked about how new information that is learned has to be acquired on a physical basis by the development of new synaptic connections between cells. That discussion is essentially the physiological underpinning of what learning is. Now let's take a basic question regarding this definition. Which of the following shows that a learning process had occurred? And the correct answer there is E, all of the above. Each of the answers, A through D, all reflect that behavior has changed because none of them are basic reflexive responses that you would see at birth. So for example, babies are not born with the reflexive ability to tie their shoes. So if you can tie your shoes, that requires learning. Babies are not born with a particular human language, so if you can speak English, that required learning. Babies are not born with a reflexive capacity to pass college algebra, although that would be nice. So if you can pass college algebra with a B+, that required learning. And the same is true with riding a two-wheeled bicycle. Human beings simply don't have a reflexive capacity to do so, so if you see the behavior occur, then it had to have occurred through a learning process. In the history of learning, we're going to start with Pavlovian conditioning, despite the fact that Pavlovian conditioning was not the first type of conditioning developed. As we'll see, classical conditioning, or Pavlovian conditioning that we're talking about now, those are two names for the same thing, started at about 1902. Two of the people that were primarily involved with it were Ivan Pavlov, whom you've probably heard of, and Ivan Tolochinov, who you probably have never heard of. Now, Pavlov was a Russian physiologist. Essentially, you would refer to him as a doctor of biology today. And he conducted a lot of biological research on the nervous system between about 1890 up until his death in 1936. Back in 1890 or so, after getting his doctoral degree, he started to work at the University of St. Petersburg. And while he was there, he did mostly work on the underlying physiological processes related to feeding and how the nervous system controlled the feeding system. So the development of saliva, swallowing reflex, the digestive process, the peripheral nerves involved in detecting food in your stomach and your intestines, and the feedback mechanisms back to your brain. All of this work should sound very biological in nature, and that's essentially what he was doing. But there was a background problem in his research that other researchers even before him had noted. And that was when you bring in your subjects to work with them in these feeding experiments, they oftentimes begin to salivate ahead of time. The dogs that he's using should salivate if he's going to feed them, but if he brings them into the room where he feeds them and they start salivating before the experiment actually begins, that salivation is actually a problem with data collection. So it was sometime around 1902 that Pavlov decided to specifically start to study how this process actually took place. And one of the individuals that worked with him was this fellow named Ivan Tolochinov. Tolochinov was a psychiatrist. He had his degree, he had a full-time position at a psychiatric center, but he would actually volunteer his time in Pavlov's laboratory just to stay abreast of the most advanced techniques in psychiatry at that time. And it was Tolochinov who literally sat in the room with the dogs during the very first conditioning experiments that we all connect with psychology today. Pavlov essentially designed the experiments, gave the work over to Tolochinov, and Tolochinov carried them out. And all of that took place around February 1902. Pavlov eventually goes on to win the Nobel Prize in 1904 for his research on digestion, but he never does win a Nobel Prize for his work in psychology, which is actually much more extensive. And there's a good reason for that. There's no such thing as a Nobel Prize in psychology, so it wouldn't have mattered what he did. There would have been no Nobel Prize for it if it was related to psychology. As Pavlov studied the processes of learning, he began to think of the associations that subjects would make similar to mental atoms. Now, the concept of mental atoms actually has a predecessor in part of Pavlov's academic work. As Pavlov was a student at the University of St. Petersburg, which is also the same place where he's going to wind up being a professor of biology, he was taught by Dmitri Mendeleev. And Dmitri Mendeleev was the chemist who created the periodic table of the elements approximately 1 decade before Pavlov got there as a student. So Pavlov sat in Mendeleev's classroom and learned chemistry and learned about the periodic table at a very early time. Later on, when Pavlov graduates and gets a position at the same university, he becomes colleagues with Mendeleev. And Pavlov's brother, Dmitri, actually becomes the laboratory assistant of Mendeleev. So Pavlov is actually very aware of the concept of atoms. When Pavlov starts studying conditioning, he starts to think of the associations that subjects make as conceptually similar to atoms. And as a result, he essentially refers to them as mental atoms. So there is a strong connection between an idea in the field of psychology in that the most basic behavioral unit of control is an association. And that association functions like its own independent entity, which would then interact with other separate entities to form other types of things. In the same way that you have separate molecules in chemistry that form together to make much larger molecules, In psychology, based on Pavlov's work, you have the idea of a basic association and other basic associations which can then be formed together to form much larger pieces of information. This concept, although it was created back sometime around the early 20th century, is actually still in use today. A lot of the specifics of it are really much more relevant for an advanced class, but to say that people in the field of learning think about basic learning processes in terms of simple associations that can be conceptualized in sets, similar to the way you think of sets of oxygen atoms and nitrogen atoms, and then oxygen and nitrogen could be formed together to create something completely different, is actually a useful theoretical understanding in psychology itself, and one that will play itself out in this particular chapter. So, in the field of conditioning, can any learning take place without associations? The answer there is definitely no, not at all. All learning must require associations. There's no such thing as behavior changing without any type of embedded association in it. And as we get more and more into the process of learning, we're going to see more and more the parameters that surround how learning takes place and how restricted you are to this general phenomenon. Now, Pavlov did a lot of the early work, not necessarily the earliest work. And after doing his work for about 20 years, he began filming it so that, sort of like an early version of YouTube, if he recorded the events in his laboratory and how the experiments took place, he could then postal mail the film footage to his friends in Warsaw or Paris. And those individuals can get an idea of how his laboratory procedures took place, and then they could copy the similar types of procedures and then send the film off to somebody else. Now, this should sound very much like the process of publicly observable and objective, the basic rules of science that we talked about in Chapter 1. And it was, in fact, the strict adherence to scientific rules that Pavlov followed that made him stand out among psychologists in the early 20th century. Despite the fact that Pavlov was a biologist and not a psychologist, he really stood out among psychologists for his work on behavior simply because he adhered to basic scientific principles, whereas in many other cases, as we've talked about earlier in the semester, psychologists had gone off on non-scientific bents and tried to address thoughts and feelings directly without evaluating behavior. Now, in this video that we have from Pavlov's laboratory that was shot sometime in the early 1920s, we're going to see three basic experimental arrangements. The first one is going to be a simulation of the original dog salivation experiments. This footage is silent, and it's going to require a little bit of explanation on my part, so I will continue to narrate as things go on. So here's a dog, and if you take a close look at the side of the dog's face, you'll notice that he's leaking from his cheek. And that's because the researchers have already done a minor surgical manipulation in which they have run the dog's salivary duct to his cheek. So that way when he salivates outside of his face. Now, the reason why they do this is so they can collect the saliva as a source of data. What they will do is they will attach a test tube to that dripping saliva that you see and measure the amount of milliliters of saliva that comes out of the dog under certain experimental conditions. So of course, as you saw the dog eating bread, the dog would eat, salivate, and then they can evaluate how much he salivates when he eats. Now, of course, there's going to be a wide variety of experimental manipulations that they can do that are going to be necessary to be evaluated. One of the ones, as you're watching this video, that you're going to see is that they will evaluate how much the dog salivates when he is given food and allowed to eat it versus being given food but not being allowed to eat it, as you just saw in that clip right there. That's a basic experimental manipulation. In any instance that the dog eats, the dog will see the food. But if he gets to eat it in one case but not in the other, then you have a measurement of the difference in the amount of salivation that occurs whether he gets to eat or does not get to eat. In most of the rest of these scenarios, you're going to see the metronome used as the primary source of stimuli that will be associated with food in these experiments. In this particular case, the metronome, which we're going to call a slow beating metronome, will be associated with food. So when the metronome runs, the dog will always be fed immediately afterward. As a result, the presence of the metronome will become associated with food, and therefore the sound of the metronome itself will cause the dog to salivate. Now, as shown here on the slide, if you continue to present the metronome but no longer feed the dog, then you are breaking the association between the metronome and the food, and the amount that the dog salivates will become less and less and less until it no longer salivates to the sound of the metronome. What you're seeing now is that the metronome runs at a much higher rate, in which case they do not feed the dog, and then they will run it at a slower rate, in which case they will feed the dog, and then they can establish what's referred to as discrimination, establishing that the dog can tell the difference between the two speeds of the metronome. Now in this scenario, they're going to switch from a dog to a monkey, but they're not going to do a salivation experiment with a monkey, which would be much more difficult and unnecessary. In this case, they're going to use gross motor behavior. When the monkey is in his cage, he likes to hang out on the upper perch. Now they're going to associate the metronome, which you see on the bottom of the screen, with the availability of a grape. So when the monkey comes down, a tray gets pushed out by the experimenter, and the monkey can grab a grape. And then he goes back up on his perch to hang out and eat it. Now, if the slow beating metronome is always associated with the availability of a grape, they can then run the metronome at a much faster speed, as you see here, 150 strokes per minute as opposed to 78 strokes per minute. If you look at the metronome, it's running very quickly. It's a little washed out because this is old black and white footage. But when it runs quickly, the monkey does not come down because no grape is ever available when the metronome runs at 150 beats per minute. But now that it runs much more slowly at 78 beats per minute, the monkey comes down immediately because a grape is always available under those conditions. Now in this case, they're going to switch over to the use of a human. In this particular case, a little boy. They're putting this headgear on him because they're going to measure jaw opening responses of the child as they associate stimulation on his wrist with the availability of a cookie that will be shot in his mouth. So that's a cookie chute. And they have these little cookies that they put into the chute, and every time the child's wrist is stimulated by a rubber bulb that you'll see in a moment, a cookie will come out of the chute, and the child will have to open his mouth to catch it so he can eat it. There's the rubber bulb. It's a very simple device. So in a separate room, the experimenter is going to squeeze a rubber bulb, which will push air through it, and that will inflate the bulb that's on the child's wrist. And that's the stimulus. Instead of using a metronome, they're using this rubber bulb on the child's wrist. That wrist stimulation is the conditional stimulus, the cue that will be associated with a cookie coming out of the chute, which you just saw. And there's the child eating. So the rubber bulb is associated with the availability of cookies. As they repeatedly stimulate the child's wrist and pair it with the availability of a cookie, each time the child's wrist is stimulated, he will automatically open his jaw with the expectation that a cookie is coming. Notice here, this is the way they collected the data back at that time on a pen and drum recorder. No questions about thoughts or feelings for the child. They're only measuring his overt behavior. Now notice in this case, the bulb is bouncing, but the child was not fed a cookie. That's called extinction. That's when you eliminate the association between the rubber bulb and the food. And as you eliminate that connection, the child will open his mouth less and less over time until finally he doesn't open his mouth at all. So you can see the bulb is bouncing. He oriented his head. He slightly opened his mouth. You're not going to see every single trial that occurs. I think in this case, he barely oriented his head. He certainly did not open his mouth. I think at this point you can say the behavior has stopped. It's extinguished. Now they're going to reestablish the association so that when they stimulate the child's wrist, cookies will then become available again. But because the child's not opening his mouth, the first cookie out of the chute will just hit him in the face. And if you look at him, he'll grab that cookie up that bounced off his face and stick it in his pocket for later. And there you can see the bulb is bouncing. Child orients his head and opens his mouth. Now they're going to go back to the metronome to finish up this series of experiments. In this case, they're going to use 78 and 150 strokes per minute again, just as they did with the dog and with the monkey. But in this particular case, they're going to reverse their value. The fast-moving metronome, 150 strokes per minute, will be associated with the availability of a cookie, and 78 strokes per minute will be associated with no cookie. Now you see the metronome is running. It's running slowly. The child is not opening his mouth. Metronome's running slowly. Child's not even orienting his head. No cookies are available at a slow beating metronome. And now when it's going to run quickly, as it starts now, he orients his head and immediately opens his mouth. So in the terminology of Pavlov, there was complete differentiation between the two stimulus conditions. A 78 beat would not be associated with food, and so the child would not open his mouth. A 150 beat stimulus was always associated with the availability of a cookie, and so the child would always orient his head and open his mouth immediately afterward. Now, as much as that might seem like simple research by today's standards, it had an enormous influence on the field of psychology as well as the field of biology, largely because at the time that this work was done in 1902 and immediately afterward, there were no experimental techniques for you to understand what effect a receptor had inside of a nonverbal animal. So for example, if you want to evaluate how good an elephant's hearing is, today it probably seems very obvious that you could just associate sounds with food and to see if the elephant is hungry, then he'll respond to the sound because he wants the food. But that process is based entirely off of Pavlov's work, which is only historically being developed at this time. Prior to this point, if you want to understand the visual acuity of a monkey or the auditory capacity of an elephant, or whether or not snakes could see outside of the visual spectrum that humans have, you simply could not do it. You could isolate what you thought was a receptor under the skin or in the eye or in the ear, but you could not trace it through the brain and figure out actually what it did. And in fact, doing so even today would be an extremely difficult task. It's much easier to use Pavlov's associative process to identify the activity of a receptor, but associate it with a pattern of behavior that would automatically be connected to stimulation from those receptors. And this is the way you would figure out whether or not deer can see in color, so hunters should wear bright orange so that other human beings could see them, but that deer can't see them. Whether or not dogs can see in color. Whether or not elephants can actually hear better than human beings. And even much more recently, in terms of this research over time, the fact that many migratory birds actually travel based upon the magnetic poles of the earth, which is a receptor that does not even exist in a human being, and no researcher would have even been looking for. But it's only through the use of Pavlovian principles in the laboratory that you can establish that some birds are actually sensitive to magnetic pathways. So what this work does, it opens up the opportunity for researchers to establish cell function in all creatures. That is sensory cell function in all creatures. So at the point of the early 20th century, the field of biology explodes in research related to sensory function. And to add to it, the work that we already covered on psychophysics, which initially got started in the 1820s and was turned into the field of psychophysics in the 1850s by Fechner, was at the root of the experimental work. So you don't just do Pavlovian research, but you mathematize the entire process and you establish the Weber function and the JND of the capacity of the subject to detect differences in the overall intensity of the stimulus. This leads to a lot of work on psychophysics, a lot of work in biology in general, and it enhances a lot of the work in the field of psychology. Not just the basic behavioral biology research, but also the idea that learning takes place through associations. Now let's take a look at this question. Which experimental methodology would eventually be developed due to Pavlov's research? And the answer there is B, habituation assessments of human babies. That might seem really odd, but when we were in the developmental chapter, we talked about how habituation was used to evaluate the cognitive structure of a nonverbal infant. That process actually came directly out of the work of reflexes and associative learning from Pavlov. Initially, the work on habituation was closely tied to the basic behavioral biology of the late 19th century, early 20th century, so that habituation experiments were used on non-humans, like laboratory animals, like dogs and rats, to evaluate what they could see and hear and how they would think and how good their memories were. That process followed through the decades unabated until sometime in the 1960s, researchers in developmental psychology suddenly realized that they could be using these animal experimentation techniques to study the cognitive structure of human babies, because from a procedural standpoint, a human baby with no language is essentially equivalent to any other animal that has no language. And as a result, these basic habituation techniques started to be applied to human babies in the 1960s, and from then, another explosion of research and development took place that was based upon all of these techniques that were originally developed at approximately 1900. Now, Pavlovian conditioning has a couple of cues that are always used: a conditional stimulus and an unconditional stimulus. The conditional stimulus is always the first cue in the pair, and the unconditional stimulus is always the second cue in the pair. The conditional stimulus is the cue that you're going to be using to try to associate with the US, in which you're going to establish that an association is created. Sometimes a conditional stimulus is referred to as a neutral stimulus. And the reason it's called a neutral stimulus is because you want to use a cue that is not active in any way, does not induce any type of behavior. It needs to be completely neutral with respect to the behavior of the animal. So for example, the metronome that we saw in the Pavlov video. The metronome is completely neutral because there's nothing about a metronome that a dog or a monkey or a little boy would automatically react to. Right? There are no basic reflexive responses that occur to a rapid clicking noise. So you can use the metronome as a neutral stimulus and then pair it with food or some other cue that does have a basic reflexive component to it, such as salivation or a hand withdrawal from being electrocuted or a startle response when a loud noise goes off behind your head and you duck your head down. Those basic reflexive responses are always going to be part of the US. Now, there are two other aspects that you have to pay attention to. These are related to responses: a conditional response and an unconditional response. And to flip back and forth with these slides, please note that the conditional stimulus that you see on the top of the screen here is always related to the conditional response that you see on the top of the screen here. And the unconditional stimulus here is always connected to the unconditional response here. So conditional stimulus, unconditional stimulus are two types of stimuli. Stimuli are physical objects in the experiment, and they are things that are controlled by the experimenter. On this slide, you have conditional response and unconditional response. Responses are always sources of data. An experimenter doesn't make a response. The experimenter can only present stimuli in the environment. It's the response that is a source of data. So the CR and the UR that you see on the screen are always the dependent measures in Pavlovian conditioning experiments. These are always the things that you're going to try to measure. So again, stimuli are things the experimenter controls. That makes them independent variables. And responses are always sources of data. Those are dependent measures that will always be measured in the experiment. Now, the response that you see to a conditional stimulus is always going to be called the conditional response. At first, a metronome, which is a conditional stimulus, will not produce salivation in a dog. But through the pairing of the metronome with the food over and over and over again, eventually the metronome will control salivation. Once the metronome does control salivation, that salivation to the metronome specifically will be referred to as a conditional response. If, however, you were presenting food to the subject, the salivation that occurs under the condition of food as a stimulus would be referred to as an unconditional response. Now, you might wonder, how can you tell the difference between a CR and a UR if they're both salivation? Well, it's the functional relationship between the stimulus and the response that's relevant in this case. If a neutral stimulus like a metronome is being played and the dog responds to it, then that response is a conditional response. But if you're actually using the food that has a natural reflexive connection to salivation, then that response is going to be considered an unconditional response. There are many different types of unconditional responses. Salivation simply was the one that Pavlov used because he had been working on the digestive tract for the decade prior to the point at which he started to study conditioning principles. As people got into other laboratories and as time went by throughout the 20th century, many other types of reflexive responses were actually used. Some you see here, such as the startle reflex after a loud noise, salivation, which was one that Pavlov used, and a hand withdrawal response after an electric shock. So if you were to put a person's hand into a glove, and that glove could be electrocuted for the purposes of the experiment, the person would always jerk their hand back, despite the fact that they're being electrocuted from the glove itself. They will still produce a natural hand withdrawal reflex. And that was something that had been used in the early 20th century. Since about the 1970s, ethical systems have kind of bolstered themselves sufficiently that it's almost impossible to electrocute undergraduates any longer. What a shame. So let's take a look at a couple of questions here. Identify the conditional stimulus from this list of possibilities. Now, you may be able to make an argument for any one of them, but there's one particular answer that is clearly the best. And that answer is C, vending machines. The reason the answer is vending machines is because a conditional stimulus is always the first of two stimuli that occur in a pair. And as far as vending machines go, you always have to see a vending machine before you can acquire the object that's inside of it, right? So you see a vending machine, you approach it, and then you get a candy bar out, or you get a soda out of it. But you always have to find it first. The presence of the vending machine always precedes your acquisition of the item from inside of it. And that produces a natural association between the visual presentation of a vending machine and the object that's inside of it. Let's take a look at one more question. Identify the conditioned response. Now, in this case, you're looking for the response that would occur to the conditional stimulus. Remember, that's always going to be the conditioned response. And the correct answer there is E, salivation to the bell after bell food pairings. I mean, I went easy on you in this particular case because we were just talking about how salivation would occur after bell food pairings or metronome food pairings. But that is the basic idea in this case. The conditional response would be salivation to the bell after bell food pairings. Now, with this basic introductory presentation of Pavlovian conditioning, we actually start to see an aspect much broader in the field of psychology that's related to many of the things that we've already covered so far this semester. The concepts of psychophysics, the concept of Gestalt, which is a context-related aspect we saw in sensation and perception, the role of attention, sensory and perceptual illusions, the role of neuroplasticity that we've been talking about on and off again since chapter 2. All of these things are basic underlying principles to all behavior. There is never any aspect of human psychology or even psychology of any organism with a nervous system that does not involve psychophysics, Gestalt, attention, sensory perceptual illusions, or neuroplasticity. They are all always there. And what you're seeing on the slide is the beginning of the recognition of a basic core set of principles that affects all of psychology. So that even though we're only halfway through the semester at this point, everything you see on the screen right now are always going to be active for every question you have regarding psychology for the rest of the semester. And in fact, in all of your more advanced classes, these aspects of behavior are always there. Now, you may take an advanced social psychology class that doesn't talk too much about psychophysics and Gestalt, but if you're a scientist and you're doing social psychological work, these are aspects that you may want to focus upon because they're part of a core set of principles. The last two bullet points, space, duration, and frequency, and symbolic meaning, are present in this chapter, but they're not typically taught here. They will show up with greater prevalence in the memory chapter. So I'm going to hold off on talking about them until we reach the memory chapter. But what you're seeing on the slide, which is very important to grasp, is that all of these principles are the essential core principles of all psychology. There is no part of psychological science that does not involve any one of these systems at all times. It's like saying you want to study chemistry, but you don't want to look at elements from the periodic table. That's just impossible. Chemistry is based off of atoms. Physics is based off of quantum mechanics. And psychology is based off of what you see on the screen. But you had to have gotten here to this chapter on learning to be able to see this all come together, because these principles of learning are all part of this system, right? Learning is one of the basic underlying principles to all of psychology, and you can never look at any aspect of human behavior without also addressing the aspect of learning. Now, the field of learning, as you might imagine, can become rather involved and very complicated, and it can. In fact, you can go through an entire doctoral program learning about learning itself without dealing with any of the other basic principles here, because there's so much to learn in this one particular area. What we're going to do in this chapter is deal with some of the most basic aspects of it so that you get a feel for how classical conditioning or basic learning operates. In this slide, we're going to look at acquisition, extinction, and spontaneous recovery as three basic underlying principles of learning. Acquisition is simply the name given to the time during which a new pattern of behavior is being developed. So, for example, in the previous movie where we had the metronome being paired with food for the dog had never salivated to the metronome before. But as we pair the metronome with the food and the dog learns to salivate more and more to the sound of the metronome, that would be called acquisition. Generally, the role of acquisition takes place until some maximal level of responding occurs where it simply levels off. Because you can't have the dog salivate to greater and greater intensity so that after 1,000 pairings of metronome and food that the dog squirts saliva from its mouth so strong that it shoots across the room, right? That's not possible. There's an upper limit to the strength of the response itself. And you'll see that when you're measuring these responses. Extinction is, as we've mentioned before, the process of breaking the link between the CS and the US. So after the metronome is paired with the food repeatedly and the dog salivates to the sound of the metronome, you then only present the metronome itself without presenting the food. That will cause the metronome to subsequently lose control over time until eventually the metronome does not cause salivation at all. You do see in this process there's something called an extinction burst. That's a bit more of a complicated process and actually is very relevant in terms of clinical psychology. But whenever a process of extinction begins, one of the first events that you see is that behavior initially becomes more intense before it starts to die off. And that's just something you can accept now. The explanation of it is related to the topography of behavior and whether or not the subject can gain access to the contingencies in the environment. It's a bit more of a complicated issue that we're not going to deal with in this class, but recognizing the presence of the extinction burst, that behavior always becomes temporarily more intense before dying out, is something that you need to be aware of. And in spontaneous recovery, what spontaneous recovery is a process by which, having fully extinguished the behavior in the middle panel, if you wait 24 hours, the behavior controlled by the CS will come back spontaneously. Now, this was actually a very odd process that took many decades to figure out. But what actually happens is, if Pavlov were pairing a metronome with food for a dog in a particular experimental scenario, one of the things that Pavlov focused on himself as a human experimenter was that he was only concerned with the metronome being paired with the food, but he discounted the role of the animal being brought into the room, which is an event that occurs once prior to the string of events where it gets exposed to metronome food pairings. Consequently, being brought into the laboratory is actually a cue further removed from the presence of food that the dog can still associate with food. And as a result, if you let a day go by and bring the dog back in, you're actually presenting a stimulus in the environment that is being brought into the room, a cue which had been associated with food. And in fact, that cue generally is only established once per day and can only be extinguished once per day. So subsequently, day by day, as you bring the dog back into the room, it always seems to reestablish some of that behavior before it dies out again. You bring them back in the following day, it brings back the behavior a little bit more, and then you can completely extinguish it that day. And if you bring the dog back in, it'll again reestablish the pattern of behavior. So you really are looking at a single trial during each 24-hour period, which causes this behavior to last into the future for a much longer period of time. This role of spontaneous recovery, as well as the aspect of extinction burst in the previous panel, both have significant roles in clinical psychology. Extinction bursts are very important in terms of eliminating behavior because they oftentimes cause bad behavior to occur more intensely initially. And spontaneous recovery is important in clinical scenarios because it's oftentimes associated with what we call emotional baggage. So that cues that are associated with an event may cause some emotional behavior later on, despite the fact that the primary cue has been extinguished. So you have a grandmother, you love your grandmother, and she passes away. Now, your grandmother's gone, but sometime in the future, you wind up seeing somebody that had the same pair of glasses on that your grandmother used to use, and you start to feel sad and you're not sure why. That's actually an aspect of what most people generally refer to as emotional baggage, but it is very much directly related to the process of spontaneous recovery. When cues are associated with each other, it turns out that similar cues that are related to the CS will also control behavior as well. And in fact, the further and further you get from the CS, the less and less likely it is that some cue will control behavior. And that should make sense. So when we talk about untrained cues controlling behavior, we're referring to a process called generalization. If, however, the untrained cues are established as non-cues for reward, then we're calling it discrimination. Generalization and discrimination are simply two ends of the same continuum. In a very general sense, if you think of the 7 primary colors of a rainbow, and you have red all the way at one end, and red is associated with food, then the subsequent colors should also control behavior, but to a lesser extent. So from red to orange to yellow to green, you should see some responding, but less responding as you go from color to color, because from red over to green, you are changing the wavelength in a systematic fashion. If you pair red with food, but the next color in the rainbow, orange, you never pair with food, you will wind up with a clear distinction, or as the formal term is, discrimination between the two cues, so that red will control a lot of salivation and orange will control none at all. And in that case, you would refer to it as discrimination. So generalization and discrimination are just 2 points along the same continuum. The reason there's a pair of twins on the screen is because if you are not familiar with these two girls, and one of them walks into the room and says, "Hi, my name is Sally," and then she walks out, and her sister Susie comes in, you'll wind up saying, "Hello, Sally," because you don't realize it's her twin. You can't tell the difference between them. If, however, you are her parent, you've seen her every day for her entire life, and you can easily tell the difference between Susie and Sally, despite the fact they are identical twins, because you're so familiar with them. And as a result, you would be said to show a clear discrimination between the children. That's just a technical term, not meaning that you treat one good and the other one bad, but that you can distinguish between two cues that are very similar to each other. Now, the role of generalization and discrimination were discovered very early in the whole process of learning. And in fact, they were focused upon by Pavlov more than anybody else back in the early 20th century. Back in the early 20th century, there's kind of a separate story that gets brought into the whole story of learning. In the early 20th century, there was a lot of debate between Freudian psychoanalysts whose theory of phobias revolved around sexual behavior and the developing theories of phobias that were created by people in the field of conditioning who believed that phobias were related to associations between two events in the environment, one possibly neutral and the other one harmful, so that if you were bitten by a snake, for example, you would develop a phobia of snakes, and then possibly even generalize that phobia to other snake or snake-like objects. So in cases like this, the debate that went on resulted in the Little Albert experiment. Now, the Little Albert experiment was not really an experiment. It really should have been called the Little Albert demonstration, because in the early 1920s, John Watson, who was actually the founder of behaviorism, you might remember that from chapter 1, was doing a lot of work on conditioning back at that time, and subsequently got involved in this debate over phobias. So what John Watson decided to do was to establish a phobic response in an infant and then eliminate it as a way to prove that he knew how phobias operated, and use that as an argument against the Freudian psychoanalytic view that phobias were based on sexual behavior. So to do this, what Watson did is he got a small child that was 8 months of old that you're going to see in this video, and he presented the child with a variety of stimuli, like a burning ball of newspaper and a dog and a monkey and a rabbit and a laboratory rat, to evaluate to see if the child showed any phobia to these stimuli, which the child does not. Watson will then pair the white rat with the sound of two metal bars being banged behind the child's head. Now, I know this sounds awfully harsh, and you could not do this for ethical reasons today, but this work was being done back in the 1920s, and there were different ethical standards back then. So Watson paired the rat, which was a CS, with a loud banging metal bars behind the child's head, which would induce a startle response. The startle response is a basic reflexive response. They'll have 6 trials like that, and then they'll bring back the rat and the rabbit and the dog and other types of furry objects to see whether or not the child shows any phobic response to them, which of course he will. So we'll get started with this video, and it is also a silent video, so I'll have to narrate a little bit to make things clear. So that is John Watson and his graduate student. Baby's reaching out to touch the ball of burning newspaper. Obviously is not afraid of it. Here they bring a monkey on a leash. The monkey is intended to be a class of stimuli of a furry object, because as I've mentioned, they are going to pair a white rat from the laboratory with the loud noises. So they're going to use a variety of furry creatures. They start with the monkey, they bring in a dog. Now, the child does not appear to be fearful of the dog. His head's back a little bit, but the dog's kind of putting his face in the dog's face. If you were looking for fear in a child, you're going to see it on the second half of this video, in which the child will be crying and trying to crawl away. That's a standard white lab rat. This work is being done at Johns Hopkins University in Baltimore, so it makes sense that's why they have a lab rat. They're just bringing one of the rats over from the psychology laboratory. And the child does not seem to show any fear to the rabbit either. Now, off the screen, unfortunately not taped, they are going to do the 6 trials of rat with loud noise. And they'll bring back the baby, and you'll see how he responds to the rat or any other animal that they had showed him. So you can see the baby's crying at this point. And he is 8 months old and kind of chubby, so I think he might have a little trouble crawling, which would be normal under cases like this. He's crying to the rabbit. He was not crying before. Watson's argument is that the fear induced by the rat noise pairings generalized to these other creatures. Now, to be perfectly honest with you, Watson did not do a very good job of establishing experimental control under these cases. That's why I say it really should not be called the Little Albert experiment. It's really more like the Little Albert demonstration. That mask has hair on it, so they considered it another furry object. But what you're seeing in this case was a scenario in which the pairing of a white rat as a neutral stimulus with a loud banging noise would induce a fear response in the child, and then that fear response seemed to generalize to other furry objects. Now let's take a look at this question. Which of the following require discrimination? Distinguishing between what? And the answer there is all of the above. Every one of these requires some degree of discrimination. Tasting the difference between skim milk and 2% milk, which I'll bet a lot of you can do. accurately identifying each of 3 triplets, your memory of a friend, and your sight of them 10 years later. If you've just gotten out of high school, there are probably some people you may not see for a good 10 years. When you see that person in 10 years, you're going to think about how you remember them, and that memory is going to be compared with the individual that's standing in front of you. And that's going to be the comparison you're making. In some cases, an individual will change so much in the 10 years after high school that you will not recognize them at all. And of course, distinguishing between Coke and Pepsi, which was an old commercial back from the 1970s. Now, there is another extension of the work that we've been involved with here. Back in the States of Consciousness chapter, we talked about how associations can be formed when you're asleep. And in fact, specifically, you can enhance the role of memory while a person sleeps if you present a cue associated with learning during REM sleep. And because that aspect actually involved a process of associations, essentially Pavlovian associations, I want to come back to just a brief clip to this older video that we've already seen so that you can look at it with fresh eyes, with the view of associations under your belt. In this particular case, as a reminder what we're going to see, an individual is learning about logic rules while a clock is making a loud ticking noise in the room. Then when the person goes to sleep and is in REM sleep, when memory is supposed to be consolidated, the sound of the clicking noise will be played through headphones to the individual, but only during REM sleep. And that should enhance the person's ability to remember the following day. And that is exactly what does happen. So what you're actually seeing is the natural association that occurs in the environment between the clicking noise and the rules of logic become established during the day and can then be used to enhance memory consolidation during REM sleep at night.
Carlisle Smith now took a daring leap. What if people could somehow be prompted to learn during dreaming? A new batch of student volunteers hear a loud clock while learning the logic game. When they're tucked in for the night, some of the subjects now wear earphones. And whenever their eyes are darting most rapidly, they get to hear ticks reminiscent of the clock. The idea is to see if the ticks remind the dreamer of the learning task right in the middle of her dream. The results were startling. Students who heard ticks during active eye movements proved far better than controls in learning the logic task, suggesting that being reminded of a problem during dreaming helps us tackle it.
So again, in this video, what you saw was the role of associations being played out in REM sleep to enhance learning. Now, one of the questions you might actually have about this is that it doesn't seem like the types of associations we had already been talking about. In the case of a clicking noise and a human being speaking logic rules, where is the unconditional stimulus? Every unconditional stimulus we've been talking about has been an electric shock or food. What type of reflexive response is connected to a clicking noise or a human voice? Well, the answer is none. In fact, what I'm doing is I'm expanding the actual way in which you should understand Pavlovian conditioning. When Pavlov started to do his work back around 1902, he did focus on the role of a reflexive response from the unconditional stimulus, mainly because he came out of this gastrointestinal research where he was using food as a stimulus to do his research. As the decades marched on through the 20th century, it became clear to learning researchers that you do not have to have a reflexive response in an unconditional stimulus, but rather the more modern, more generalized view of learning is that you simply have to have two stimuli, and neither one of them has to have a reflexive component to it. So if there are just two sounds in the environment, like the sound of a clicking clock and a person speaking, those two things will simply become associated together. And as a result, when you start to evaluate what kinds of things are linked together, you're going to notice that of your six senses, remember balance is your sixth sense, all possible combinations of your six senses appear to be associated together, like hearing and sight, hearing and taste, hearing and smell, and so on. And all the various combinations of your six senses are all establishing associations in your brain moment by moment, whether you are awake or whether you are asleep. And we'll see when we get to the memory chapter that only some of these associations start to become enhanced and show up in your conscious awareness as a direct result of their use in terms of feedback loops between you and the environment. And then you'll actually start to see why it is that some things you focus on and other things you completely ignore. It's related to the sum of all of the associations you make, whether you are awake or asleep, because you can never turn off your sensory system, and which of these associations are actually most relevant for you given the environmental conditions that are occurring at any one moment in time. And that concludes this portion of the introduction and Pavlovian conditioning component. Please move on to the operant conditioning section next.